Whether you've done a titration before or if this is new to you, it's still really important that you review that short clip that I sent you as a preliminary video for these lectures. It's really critical that you know what a titration is. We're going to be performing calculations surrounding them, and so to be able to envision what's going on is going to make a huge difference as to how successful you are performing these calculations. It's really important that you understand that a titration is an experimental way of determining the molarity of a solution of acid or base by performing a neutralization reaction using a solution of known molarity. There are 4 major types of titrations that can generally occur. You can titrate a strong acid with a strong base, a weak acid with a strong base with a strong acid, or a weak base with a strong acid. To mix 2 weak components together is possible, but it's not very useful because they both have ionization constants. And a titration, if you remember, is a lab. You design it. So it makes more sense to select a component that's strong and will be a little bit more definitive for your results. Okay. When a titration is performed, which you hopefully saw in the video, you're going to wind up with a graph that looks like this. Okay. In this graph, you can see that at the bottom, we've got the volume of the NaOH added. That would be your titrant. So in this case, we've been adding a strong base. You can also tell that a strong acid was the original component of the flask in the titration because our original pH is a 1, and that's on the acidic end of the scale. Okay. A couple more things to look at when you look at this graph. We did say that the initial pH was a 1, but it's also important to look at the initial change in pH, which in this case is very, very insignificant. Even after about, I would say, 5 milliliters of NaOH have been added, there really isn't a great change in pH, which means that the solution that's in the flask was initially very capable of resisting a change in pH. That's a good indication that it was a strong solution. Okay. All right, as we move on in the graph, you can see that we get to about here, and at this point, a little bit over 20 milliliters, we start getting this very, very rapid change in pH. This is due to the fact that all of the strong acid that we had over here is now pretty much neutralized. Now what we're doing is adding in strong base, and that's sort of taking over what the pH of the system is. So in pretty much every titration, you're going to get one of these vertical lines. Halfway up that vertical line, you're going to get something called the equivalence point. Okay. And the equivalence point for this particular graph is at 7. A pH of 7, and that's pretty important. You're only going to get an equivalence point at a pH of 7 if you're titrating a strong acid with a strong base or a strong base with a strong acid. It will not be that case if there's a weak electrolyte involved. Okay? So we have our equivalence point here, okay? And as we move up the graph, as we add in maybe just a couple more drops of NaOH, we're going to get up here to a more basic pH, and it's going to plateau. So that's what's happening. We're adding in a little base down here. Okay. And right about here, we finally start changing our pH. We can continue on and get ourselves up to the equivalence point. Okay. And like we said, our clues that this was a strong acid have to do with the fact that we had an initially slow change in pH. We had a very low pH to start with, and we have an equivalence point at 7. There's one more point on this curve that's really important. It's called the halfway point, and it really doesn't appear on this particular graph because it's something that you will see more with a weak acid or a weak base. Okay, but it's called the halfway point, and it exists between your initial pH and your equivalence point. So it's going to be, I don't know, on this graph I would say right about here maybe. So that would be your halfway point. It doesn't appear on a strong acid, strong base graph, but if it were to, if this were to be a weak acid graph, the neat part about the halfway point is at that point, the pH that you have is going to equal your pKa. Okay, so at the halfway point, the pH equals the pKa. Just really valuable information, as you can see, because once you get a titration curve, if you can pull the Ka out of the pKa at the halfway point, then you can start doing an icebox and start performing some of the calculations that we're used to. Okay, so equivalence point, halfway point, initial pH. Okay. And one more thing that's worth pointing out is this region in here is considered the buffer zone because we don't really have a change in pH. It's still resisting, it's still buffering against that change in pH. All right, let's take a look at a few more graphs. Here's a little bit of what I just said if you want to just do a quick review. Okay. All right, so some more graphs. So up here what we have is we have a strong acid being titrated with a strong base. Here we have a strong base being titrated with a strong acid. And you can see in both cases we have an equivalence point of 7. Okay. We have initially a slow and gradual change in pH. We have a very low pH here. We have a very high pH here. So we know that they're both strong. Okay. Let's look down at some of these curves down below. So if we look at this one right here, this one begins as a weak acid being in our flask. And I can tell that for a couple of reasons. First of all, if we look at the initial pH, it's a little bit higher than it was with the strong acid, but that's a relative thing. But if you look here, we have this little bump up that exists. That bump exists because it is a weak acid that's in the flask, which means that it's going to be hard for it to resist a change in pH initially. Okay, so you're going to have this bump up where the pH changes sort of dramatically. And that's not a vertical line. That's part of the initial portion of the titration. As you move along the curve, we'll get up to our equivalence point. At this equivalence point, you can see that it's at about 8. Okay. The equivalence point is going to be greater than 7 if it's a weak acid being titrated with a strong base. Okay, because you've added in so much base that the equivalence point is going to occur at the more basic end of the scale. Okay. And you can see that we've got the halfway point right about there, and that's where you would find the pH that equals our pKa. Okay. So over here we've got a weak base, and you can see that there's a slight dip. Okay. There's a slight dip to begin this one. And so that's sort of indicative of the fact that it was a weak base. It didn't resist the initial changes in pH. And again, if we go over to our equivalence point, okay, you can see that our equivalence point over here is something less than 7. There's our 7 right there. Here's our equivalence point here. Okay. So it's going to be something less than 7. Okay. So equivalence point, initial pHs, shape of the curve, those are a few things to look at when you're looking at these titration curves. Okay. All right, let's take a look at one more graph. If we look at this graph up here, we can see that it's got 2 vertical regions, one here, one here. Okay. This is because it begins as H2CO3, and it's going to go through a stepwise dissociation, HCO3 minus down to CO3 2 minus. Okay. And each of those steps is going to have its own sort of titration curve. There's one there, and here's one here. Okay. They're each going to have their own halfway points. Okay. They're each going to have their own equivalence points. Okay. And as a result, they're each going to require their own indicator solution to indicate their specific equivalence points. Okay. So if you see a titration curve with multiple bumps, it's because you've had some sort of stepwise dissociation, whether it's from an acid or a base. Okay. All right. Let's look down. I wanted to include also this graph, this chart, which is from your book. This shows a bunch of different indicator solutions, and it shows the different pHs at which they change color. So you can see that the equivalence point up here is somewhere below, probably around 8. Maybe it's actually right about there. So they selected an indicator solution that had a pH in that region. Okay. And up here, they selected phenolphthalein because the equivalence point is somewhere in the range of where phenolphthalein would indicate. All right, we will talk a lot more about indicators later on because we need to be able to do some calculations surrounding their own equilibrium that they perform. Okay. But I want to take a look at a problem real quick. All right, consider the titration of 100 milliliters of 1 molar HCl with 0.5 molar NaOH. Calculate the H plus in the solution after 50 milliliters of 0.5 molar NaOH have been added. All right, your first step in this problem is really just to calculate the number of moles we have of each of these components. Okay, so if we're going to take the volume and the molarity, we can use those to calculate the number of moles. And ultimately, that's going to give us, let's see, point HCl, moles of HCl. And we're going to find that we have 0.025 NaOH. Okay. So down below here, we would do a before and after table, and the equation that we're going to have really, if we get rid of all of our spectator ions, is just H plus OH minus goes to water. Okay, we've got our before, we've got our after. We calculated above what our before concentrations would be. Okay. Our change is really just going to be that this is going to get eliminated, it's going to get neutralized. So we're going to have an after of 0.075 for the H plus and 0 for the OH minus. We ignore water the whole way down. So this is kind of important. For the next calculation, it's important to realize that there's going to be a new volume. Okay, so we have a new concentration, our new number of moles, 0.075. But because we've added two solutions together, we have a new volume. And that's going to be a theme through many of these problems. So we've added in 50 milliliters to 100 milliliters. So we're going to have 150, which is going to give us a concentration of 0.5. Okay? Which is ultimately going to give us a pH of 0.3. So this is a pretty straightforward problem, but I want to use it to draw your attention to the idea of the changing volume right here, okay, and the fact that a neutralization reaction occurs, and you have to do stoichiometry prior to finishing up the problem. Okay. Stoichiometry is going to be part of every single titration problem that you do. Equilibrium is sometimes a part of the titration problems that you do, not always. Okay. All right, let's look at a way that these problems are normally presented. I'm going to do that in the next video, so pause this real quick, and we'll come back.